to do is you have to increase the granular surface thickness. So what we do is we increase the thickness to 250. If we increase to 230, let us try what is that 230. So let us try with 250. So now I increase my granular layer GSB layer to 250. Okay. So everything remains same except my analysis depths will change now. So analysis depths will change to 250 and 250, and run the analysis, and I want to see the results here, and I'm interested in what we call, I'm giving the commentary so that you will be familiarized with the terminology. I want to see, sorry. So I want to see what is the compressive.
What about radial depth for 250 mm thickness?
Sorry, say that again.
What about a radial depth for 250 mm thickness?
No, radial distance. Radial distance will remain same. You always want at the center of the dual wheel and the center of the one of the ties. The only depth will change. Depth will be because, see, let me show you.
The MPA also will be changed, right, or no?
What?
MPA, this one, the residual modulus.
Yes, that will also change. So now it has become 250. Okay, and the elastic modulus will also change. So now what is the elastic modulus? 0.2 multiplied by h power 0.45 multiplied by 50. H is now 250. Can you help me? How much is this value?
$119.
So okay, so I'm taking it as 120 just so that we can remember. So if we input elastic modulus of 120 and the depth as I was saying, because 250. So my now the new coordinates will be the radial distance. Maybe I will put z first. 250 comma 0. This is radial distance. This is z. The second coordinate will be 250 comma 155. Okay, these are my radial coordinates for new one. So if I submit and run, so what I have to look is z value, which is maximum of these two values, which is here it is 2166 micron and 2056 micron. Okay, so what was the someone can write down is 205, the maximum is 2166 micron. Okay, maybe I'll also write down somewhere. Two 166 micron. So what is the allowable we were talking about earlier? Allowable strain. Allowable strain is 2433.
Yeah.
So 2433 is more than obviously 2166 is less than 2.2433. So So the 250 is okay. Okay. So there are two terms which you should be comfortable with by now for you to able to understand what we are discussing. So there are two ways you can compare whether your design is correct. So either you input your design life here and find out the allowable strain, okay, and other way around is you whatever the strain you are getting, you input into this one and find out for that payment section what is the allowable MSA, allowable traffic, or allowable standard access numbers, so either you do this thing, whichever you are comfortable with, you can perform, but we will be discussing both of them so that you are convergent with both of them, both the approaches. So I hope everyone is clear about this thing. So what I'll do now is there are a few one or two aspects I want to discuss before we start designing the conventional payment design approach.
Sir,
Yes.
sir, where we will found very low volume traffic, and our MSA will be less than 20. Then which formula to be adopted? Whether we will
So
go for the
according to IRC
10,000 cycle
120, so I discussed this yesterday, so you can see here. So less than 20 MSA. Sorry. So reliability, you have to use 90% one. If it is expressways, national highways, and standard highways. Okay. If it is 80% for other roads. Okay. For other roads, it is 80%, and for national highways and expressways and state highways, it is always 90%. Okay. So this equation is 90% reliability. This equation is 80%. Hope this is clear. Let me discuss a few things before we start.
Sir, for 80% reliability, 10,000 cycle will be there or any changes?
No, still it is 10,000 cycles.
Okay.
The cycles will remain. That is your design parameter, isn't it? That will not change. But if you input your strain, whatever strain you are getting, it will give higher value. For example, whatever the for 150 strain we got 42, 4324 or some strain. If you input that into 80% reliability, you might have got 10,000 cycles. Okay. So we discussed this.
Yeah.
I'll discuss it.
Okay.
Yes, please.
I am having one question regarding the output file of the IIT-PAVE. When you said the EPZ value with that
Okay,
250L, suppose 250L and 250L, there are two, right? One is at 0 and one is at radial 155, right? The EPZ, which value we should consider? I'm asking you, the 2166 or 2056?
No, maximum of those two.
Means maximum is we need to not consider that negative, right? Only maximum these two
No,
values.
always we should select absolute number. Okay.
Okay.
Whether you are considering the number or whether you are even if you are inputting into those fatigue equation, it is always absolute number.
Okay.
Okay. So that negative and positive is a sign convention. It is just a sign convention. Negative is compression, positive is tension. It is just a sign convention, nothing else.
Oh, okay. So here we take like 2166, right?
No. So it is 2166 multiplied by 10 power minus 2, isn't it?
Yeah.
So it is 0.002166.
Yeah. So we will be using this value, right? I'm asking the maximum of this.
Yeah, which is 0.002166 you should be using.
Yeah.
So which is 2166 micron.
Yeah.
Because we are familiar with micron, we always talk in microns and MSAs. But actually, we should be using the actual strain value.
Okay.
Okay.
Yeah.
So I will talk about CTSB bit later. Okay, when maybe when I'm discussing the CTSB example pavement design, I'll talk about CTSB and granular subbase. With the geosynthetics, we will discuss later. I'll talk about when I'm talking about design of pavement with granular geosynthetics. I will discuss that. Okay, which might not take long time. Only 5 or 10 minutes it will take. So now coming to the granular base. This is when using CTSB, the granular base modulus has to be 350, which I will anyway discuss later. So the effective modulus of these all points are when you are using CTSB, when you are using GSB. So basically the important point you have to remember is when we are doing the conventional pavement design, when we are performing conventional pavement design, you will analyze as a three layers. Okay, this is bituminous layers. Okay, this is unbound granular layers, and this is subgrade. So you consider these two is granular layers means GSB plus granular base. Okay, you consider the thickness in MR calculation, you consider these two thicknesses as H. Okay, if you remember, we talked about E equal to or MR for granular is equal to 0.2 multiplied by H power 0.45 multiplied by M support. So this H is thickness of this both granular base and granular subbase. Okay, and obviously M support is the subgrade modulus. That is clear. And let me discuss about the bituminous layers first, so that I immediately after this thing I can discuss about the conventional pavement design. So what IRC suggests is, if your traffic is more than 50 MSA, the recommended surface course mixes is SMA, gap graded rubberized mix, and bituminous concrete with modified bitumen. Okay. So if it is between 20 to 50 MSA, it is SMA, gap graded rubberized mix, and BC with modified binders, or BC with VG40 is also allowed if it is 20 to 50 MSA. Okay, other mixes is allowed if it is less than 20 MSA. So for bituminous surfacing with less than 40 mm, if your design suggests it is less than 40 mm, you should use VG30 instead of VG40, because what happens is it is slightly more flexible, VG31, because thinner layers. So I'm talking about only bituminous, not surface course. Entire bituminous layer thickness has come less than 40 mm, then you should be using VG30, not VG40. Okay. Obviously, in snowbound locations, very cold areas, you rather use VG10 rather than VG30 and VG40 for fatigue reasons. So if you are having very stiff bituminous layer, it tends to crack if it is very close.
VG30.
Sorry?
Sir, can you please again repeat that VG30 and VG40 applicability?
So VG40 is allowed to use if your traffic is between 20 to 40 MSA. BC with VG40 is allowed. Okay, if it is less than 20, BC with VG40 is allowed along with other mixes. But if your total bituminous thickness, say for example, you run the analysis, Okay, your traffic is something like 10 MSA or 5 MSA, something like that on a national highway. And for that, when you run the analysis, the bituminous thickness has come only say 30 mm thickness. Okay, then in such cases, you rather prefer to use VG30 rather than VG40. The reason is, if you have very thin layers, usually the strain, the failure mechanism is slightly different. So you want the material that is more flexible. Okay, that's why we use VG30 rather than VG40. Okay, obviously in slow bound, because you do not want very stiff material in a like very cold regions. If you have very stiff material, it tends to crack. That's why in cold regions we use VG30. So bituminous layers, okay, base and binder course, DBM, obviously the base and binder course, it is DBM. Anyone has asked some question?
Sir, is there any circular from MOT that the minimum thickness of this BC layer or the total BC layer should not be less than 40 mm? It should be the minimum.
Circular?
The minimum thickness of the BC layer should be 40 mm. Is there any circular from MOT?
I don't know. Is there any circular?
Because when we have submitted the estimate with 30 mm BC, it was rejected, saying that there is some circular from MOT that the minimum thickness should be 40 mm.
Okay, the which I do not know, but
no, circular is such that if you are going to only BC overlay only, you have to use the minimum thickness of 40 mm.
Say that again.
In the case of BC renewal only, BC relay only, it's a circular, the minimum thickness should be 40 mm.
Okay, if you are that is for renewal schemes.
If you are going for BM and BC, then you can use the minimum thickness should be BC should be 30 mm. That's
okay.
Okay, sir. Okay, sir.
So who was that answering actually?
Chief Engineer.
Okay, thank you very much. Okay, so the IRC 37, what it suggests is DBM with VG40 for greater than 50 MSA and VG40 DBM, dense bituminous spectrum, if it is as a binder and base courses. This is the allowable binder and base courses is always DBM. Okay, but you can use VG30 or bituminous macadam with VG30 if your traffic is less than 30 MSA. Okay, you have multiple surface course option, but the base course in most cases it is DBM, but you can also use bituminous macadam. Anyway, nowadays no one is I don't know, but as far as I know, the projects and I know they are not using BM, but in some states if they I don't know, but generally it is DBM. Okay, so another clause that was highlighted in IRC 30 is although VG say if you have looked into IS 73, there is some overlap between VG30 and VG40. To avoid some confusion or misuse of the bitumen grade, it recommends to choose a bitumen that is greater than 3600 poise viscosity. Okay, so this is one point. So this is, you can see, this is a summary table. So which bitumen type? So mixed type is a DBM with VG40 if it is greater than 50. Bitumen type can be modified bitumen if it is for the SMA. Crumb rubber modified bitumen, obviously gap graded rubber. It is polymer modified, should say. This is crumb rubber modified. BC you can use with modified bitumen as well for 50 greater than 50. Surface course. This table is in IRC as well. Okay. Again, SMA modified bitumen polymer modified bitumen, we should say. Also, we can use crumb rubber modified as well. Gap graded rubberized bitumen, which is crumb rubber modified bitumen, and a BC with modified. So this is what we discussed anyway. And it also suggested some modulus values. But as I was saying, the most important one we are in most of the cases, it is 35 degrees C. Okay. So the most cases we see is BC and dBm. Maybe I think I might have using the so hopefully you can see this one. So you have to, usually the cases will be 3000 dBm, PC and dBm, it is 3000 megapascals if you are using VG40. If you are bitumen you are using is VG30, it is 2000 megapascal. Okay, and if you are using the VG10, it is BM bituminous magnum, it is 500. Anyway, these two we will rarely get, but the stabilized basis you have to use 800 megapascal. So one point you have to remember is, so if you are running, as I was saying, you consider as a bituminous layer is one single layer. So which is the, we always choose the, say for example, let me explain this point, and after this point you can break for a few minutes, which is slightly important and maybe may require some clarification as well. So as I was saying, for a bituminous design, so this is bituminous layer. Obviously you can have multiple layers. Maybe you can have SMA, stone matrix asphalt here, and DBM here. Okay, and you have granular layers and other things. So we always use the modulus of this layer. Okay, DBM layer, whatever the modulus. So DBM layer with VG40 modulus is 3000 megapascal. We will be using. Although SMA might get less or more stiffness, but that is different discussion. But always we use the elastic modulus of that layer. So maybe we can break for 10 minutes. So in my computer it is 11:28. Maybe we can come back at 11:40. Okay, 11:40. Once we are back, what we'll do is we will I will show the design for a pavement using IIT-PAVE, the conventional pavement. So we learned few things so far. One is I think you are now familiar with how to choose the locations, modulus values, conversion. Most of the basics required we have learned, and we have learned how to get the effective modulus of the subgrade, and we also learned how to check the granular subbase thickness using IIT-PAVE. And the see, one point you have to remember is IIT-PAVE is the least important thing in IIT, pavement design. Okay, it gives whatever the output depends on whatever the input you are giving. So the most important thing is you have to know what inputs are given. So and also you have to have some judgment. Okay, when you are selecting the material inputs and everything. So do not make the IIT-PAVE as like most important thing. Okay, that is the as far as me, like it is the least important thing, because it will only run, it will not know whether you are giving it is a cement treated base or granular sub base. Okay, it doesn't know. You are giving some numbers, it is assuming that numbers you have given it is correct, and it is giving the output whatever you are asking for. Okay, so you be careful when you are inputting the these values. Okay, whatever values you give, you will get some values. Okay, so That you have to keep in mind. So if you have any questions, I can answer your questions. Others, if you do not have any questions, you can leave and you can come back at 11:40. Any questions for others?
Sir, today's beginning, the first example, we have taken 40,000 kilonewton, 40 kilonewton load as a wheel load. And the reason
40
was
kilonewton load?
40 kilonewton load as a wheel load.
Mm-hmm.
And the reason was there is effective CBR. Am I right?
For effective CBR, basically what we do is, so for effective CBR analysis, we take it as a single wheel load. So single wheel load with 40 kilonewton. Okay.
Sir.
If you are running for other analysis, you consider it as a two wheel loads, each carrying 20 kilonewton. This one is carrying 20, this one is carrying 20. Okay. What is your question now?
CBR. And other analysis, if we have to take effective CBR, I mean our CBR is not sufficient, that time also we will a single load of 40 Newton or dual wheel load of 20 kilonewton each.
No. See, only when you are determining effective CBR,
Sir.
In all other cases, you will take 20 kilonewton. Dual wheel, 20 kilonewton. Only for effective CBR calculation, you take 40 kilonewton single wheel load.
Okay. Another thing, sir, annual average temperature, how we'll calculate this for bitumen? VG30 and VG40 are shown. Annual average temperature of more than 3000 centigrade.
Say that again.
That annual average temperature of 3000 for VG30 or 40. From where we'll get it?
No. What is it? 3000?
That annual average temperature you have shown in a table.
No. That is not temperature. That is what I was wondering. So that is elastic modulus.
Achha.
So what I have shown is, so elastic modulus. So this temperature 35. So I'll show you what I no, that
There is temperature
in all cases. So for the climate, you can see this one. For climatic condition prevailing in plains of India, the annual average is expected to close to 35%, 35 degrees centigrade. So you have to calculate. There are equations available in these guidelines and as well in other guidelines as well. Some references are given in IS 73 as well. But in most cases, we take 35 except in some locations.
No, sir.
So for snow-bound areas, resilient modulus, we take for the 20 degrees. But all other cases, we take 35 degrees. The resilient modulus values for 35 degrees. Okay.
In all it is written average annual pavement temperature. So that 1000, 3000, 35 degrees centigrade.
No, those is no. So see, this is, I think you are right. So if your annual pavement temperature is 35, the elastic modulus, which is resilient modulus, is these values. All these are resilient modulus, indicative values of resilient modulus in megapascal for bituminous mixes, because bituminous mixes are viscoelastic materials, so they are temperature dependent. So if your pavement temperature, which is for Indian conditions, we take it as a 35 as a constant value. So if it at 35 degrees centigrade, your BC with dBm will have 3000 megapascal stiffness. Okay, if it is dBm with VG30, it will have around 2000 megapascals. Okay, if it is Vg10, 1000 megapascal. So these are the values we have to use for the analysis. Of course, maybe there is another table. Here, so it is clearly says bituminous. So for the analysis, structural analysis, bituminous layers with Vg40 or modified bitumen, you have to take 3000 megapascals or the tested value. So if you if you have carried out resilient modulus test and if you found it is 2500, you have to use the whichever is the less value and the Poisson ratio as 0.35. If for bituminous layers with Vg30 it is 2000. Okay, for unbound granular layers you have to use that 0.2 multiplied by h into 0.45, that equation. Okay, and it has given the modulus values you have to choose. Okay, is that answer, does that answer your question?
Yes, sir. Thank you.
Okay, I'll be on mute and I'll come in 2-3 minutes. Okay.
इस पर सब आएगा, इस सब क्रांति कुना, यही मीटिंग ले रहे हैं, भाषण दे रहे हैं। हाँ, कुछ पूछा रहा है, वीडियो करे, वीडियो करो ना। आवाज कहाँ है? आवाज करो, वीडियो हटो। बाद में वो सब जो बोलेगा से उस पर आवेगा। हमको पता, हमें तो पहले पता जो इसमें बोल अब आप बोल सकते हो, आपका आवाज हो जाएगा।
So one thing I was discussing during break is this table. Okay, you can refer to this table in most of the cases. So this will be useful. Whatever I'm discussing is useful when we are discussing the example as well now. So the bituminous layer modulus, we have to take 3000 megapascal. But if you carried the resilient modulus test and found out that that value is less than 3000 megapascal, obviously you have to choose that the lower value, whichever is the less. Say for example, if you get 3500 as well, still you have to use 3000. Okay. Similarly, for if you are having Vg30 bitumen in your DBM, okay, which is obviously not in one of the cases it is allowed. So then in that case you have to use 2000 megapascal. Similarly, obviously for granular layer we use that 0.2 multiplied the equation. And the Poisson ratios you can see, except for cement treated base and cement treated subbase, the all Poisson ratios values will be 0.25. Okay, you can remember that. So now let us do a payment design. Okay, again the example that we have in IRC. That is okay. So this is the example, same example taken from IRC 37. Okay. So you have a four lane divided carriageway. Okay. So what is the importance of saying whether it is a 4-lane or 6-lane divided carriageway? What information we can obtain from this one? Obviously, what we are designing is design of a bituminous pavement with a granular base and sub-base layer using input layer. So it is a conventional, fully flexible pavement. Okay. So what information we get from this one? This is important for
directional distribution.
Lane distribution factors. Okay, you can go and check what are the lane distribution factors if you're. And what is A? So A is what is, yes, so the traffic at the end of the construction. Okay, that is A. So that is like if you are opening your payment from tomorrow, what is the traffic today? That is A. So which is 5,000 commercial vehicles per day. And R is 6%, which is growth factor is 6%. Design period, you are designing the payment for 20 years, and you can take VDF. I have discussed how we can calculate the VDF, but I will also discuss maybe after this example. I will show you how we can calculate the VDF from a axial load spectrum. Okay, and the same for both direction, assume. And directional distribution of the traffic is 50-50%, assume that is an assumption. Effective subgrade is 77%. Okay, and we also need some other data. If we discuss it for the fatigue equation, we need air void content information, which is 3%, and also volume of the bitumen content, which we require is 11%. Okay, this information is given. So now what is the first thing we have to do? Okay, we are interested in two things with this one. Okay, one is inputs for, maybe I'll write here. So input for those performance models, and also another inputs for the IIT-PAVE. Okay, now for obviously performance model, we need either NF or NR and N fatigue. Okay, because it is conventional payment. So NF is number of cycles to design traffic. So how we can calculate the design traffic? So we have this expression, if you remember. So we have this expression 2,500 because 50% we have. You can work out along with me so that you can get 2,000. You can get down. So 50% directional traffic. Okay, which is 5,000 is the cumulative vehicles per day. 50-50 is 2,500. 365 multiplied by that A value 1. We gave R. This is R value 0.06. This is also R, and this is N, which is design life minus 1. 0.75 is for 4-lane divided carriageway. The lane distribution factor we discussed, it is 0.75, and VDF, okay, which is F vehicle damage factor, which is 5.2. If you multiply, this is 131 million standard axis. Okay, so if you input this 131 million standard axles into you can help me with this one. This one. So this is information we need. So you can tell me now. Let me clear this one. So what you can do is you can input that NF, so which is 131 million standard axis, so or 131 with 6 zeros into these two equations. Okay, oh sorry, because we are interested in only this equation, and also this equation. So maybe you can start inputting that 131 million standard axis. So million is 10 power 6 into NR, and can you tell me what is the EV you are getting, allowable strain? So easiest thing is maybe you practice this one, how you can do by using pen and paper, but the easiest thing to do is you prepare an Excel sheet. So I have got an Excel sheet. I can send it to you as well. So I have, I think this is the example. So what I have got is I have input everything into this one. So 131, and air voids, if you see from the air voids we are discussing, it is 3% air voids. Effective volume of the bitumen is given 11.5. Okay, so what is this one? M value, if you remember from this expression, M is 4.84. Just give me 1 second.
And max value of bitumen content.
Sorry, say that again.
what should be the minimum and maximum pavement content, and what's its impact on flexible pavement design?
Minimum values for BC and DBM are given in the respective IRC codes, isn't it? For DBM 1, I think it is 4.7. So sorry, for DBM 2, it is 4.7% bitumen. For DBM 1, I think it is 4. I might be wrong, but the values are given in the respective codes. What is the minimum bitumen content? Okay. And also BC, I think BC it is 5% or 5.2%. Around this number. For DBM it is slightly less, 4.5, 4.7, and BC I think it is 5 and 5.2. I might be wrong, but it is given in MORTH, it is given. Okay.
Yes.
And coming to
what would be impact on flexible pavement?
That is what I'm going to say. So you can tell me based on whatever I have discussed so far, what is the impact? Is there, you can see that for expression here. So now you see this, I already discussed actually. We have M parameter. The amount of bitumen is this VBE, effective bitumen volume. Obviously, if you are putting more bitumen, the volume of the bitumen will be more. Okay. If this value is more, your M value will be more. If your M value is more, okay. So where is this? Your C value will be more. If your C value is more, your number of cycles for fatigue failure will be more. So you are obviously what IRC 37 suggesting is, obviously you have to design. It also, there is some recommendations on how to design this. We call it as a bottom ridge layer. Okay, bitumen bottom ridge bituminous layer, in which you have to design for 3 or 3.5% air voids, rather than conventionally we design for 4.4% air voids, but here we have to design 3 or 3.5 air voids. Okay, that means you are inputting the air voids. So what does that mean? If you are putting more bitumen, obviously we should not be compromising on other properties of the asphalt mix, such as rutting and maybe bleeding as well. If you do not compromise, if you put more bitumen, usually your fatigue life will be more, according to IRC 37, because your VBE is more. If you are putting more bitumen, your VBE will be more. And if your VBE is more, your M will be more. If M is more, your C value will be more. If your C value is more, your number of cycles to failure for a particular strain value is more. Okay. So does that answer your question? Okay, no problem.
I would like to have, I'm having one question.
Yes.
See, now you are taking this air void and the effective bitumen, right? This will be done during the design mix, right?
During the mix design, yes.
But most of the time, what happens? We have to give the
You will not have this
advance.
thing. That is true. So that's why the indicative values were also provided within the IRC 37. So you can choose 11.5 and air voids of 3.5% during the design period.
Okay.
Okay.
And
so
this
you
should
will not have.
And this should be satisfied during the what is a design mix, right? Minimum.
I mean, see, it is difficult to satisfy, but you can slightly modify these things. Okay. Design later.
Okay.
No, if it is more, it is okay. So that's why during the design period, you can be little bit conservative.
Okay.
Okay. Say for that will be a problem for many other cases. Say for example, now you are designing for assuming a modulus value of 3000 for VG40 bitumen. Say for example, now you carried out resilient modulus. You have got only 2800 megapascal stiffness. Then what would you do? You have to change the design, but rather than doing that, even the same with the volumes, you can be slightly conservative, taking the indicative values in the beginning. Okay.
Okay.
But this is the design approach. Okay. Can you just for now, if you, we know it is 131 million standard axle for this pavement design problem. Can you tell me what is the allowable tensile strain? Okay, if you are, the easiest thing is, as I was saying, to develop an Excel sheet. But for now, because you do not have an Excel sheet, I can share this one with you. Now I can message this. But the other thing you can do is, let us do the analysis and you input the strain value and get the whether that is satisfied or not. Maybe let me share this one with you. So someone has done this for me.
Please share in WhatsApp. Can I download?
I think I can share in this message as well. I think so. But you can develop your own. Let me. Can I not share using this one? Okay, I think this option is not there. But it's okay. This is a very straightforward Excel sheet which we just input the formula. I will, when I'm sending the lecture slides, I will share that one with you. So let us run the IIT-PAVE analysis. But before that, we need some more information. What additional information we need for IIT-PAVE analysis? Okay, so we need subgrade modulus. We know it is 62 megapascal because our subgrade is 7% CBR. Okay, and granular layer is 62 multiplied 0.2 multiplied by H, which is, so before that what we can do is, so did you note down the values? Okay, so let us assume, say I need, maybe easiest thing to do is, I'll tell you what it is. Okay, so 100, I'm assuming 190 mm of bituminous layer. Okay. Maybe I can choose so let me see an example what they have taken. So 250. So in example, 230 is the granular base, 230 is 250 is granular subbase, and 230 is granular base. Okay. So now this is elastic modulus is 3000 megapascal. Okay, the elastic modulus for this one, how much did we get from? I think 200 megapascal. Okay. And subgrade elastic modulus 62 megapascals. So is that clear how we got these numbers? Just ask me now if you have any issues. Okay, 3000 megapascal, we take it from IRC 37, 200, we calculated from the thickness because our thickness is 480. So it is 480 together, 480 mm. So MR granular equal to 0.2 multiplied by 480 power 0.45 multiplied by 62. Isn't it? This is H value. So we should get 200. You can check if you. Okay. and this one we already got input. So that 17.6 multiplied by CBR 7% is 0.64. Okay, this will be 62, which is a MR of subgrade or support here. Okay, so this is okay. What other information is required for us to run the analysis now? So now we have a trial thicknesses. First thing we need to assume some trial thicknesses. I'm assuming 190 bituminous layer, 480 granular layer, and 62 megapascal subgrade, which is infinite. And I got 200 megapascal granular layer and 3000. What other information is required? Obviously, I will have a dual wheel here.
No.
Can you tell me what other information is required? So we need the at what locations we want. So coordinates. Okay. So we are interested in strain values, tensile strain values at this location and this coordinate, these two coordinates, and compressive strain values at these two coordinates. Okay. Epsilon V at these two coordinates and epsilon T at these two coordinates. Can you help me out in telling me the coordinates? Say for example, this is 1, maybe this is 1, this is 2, this is 3, and this is 4. Can you help me out in writing down the coordinates?
One is 0, 1, 0, 190.
So first one is let us write a radial distance first. Radial distance for this one is maybe let me write depth first and radial distance later. Okay, coordinate 1. What is the depth?
190.
It is not 0. 190 and 0 in mm, obviously. Radial coordinate for the 2.
190, 155.
Okay, 190 and 155. And radial coordinate 3.
It is 480
so
plus
it is 190 plus 480.
Yeah.
How much is that one? 670?
You are calling is out of network coverage area.
670 and 0. And radial coordinate 4 is?
670 and 155.
155. So we have all the information, and obviously we'll give a wheel load of 20 kilonewton and a stress of 0.56 megapascal. Okay, so this is the information we need. So we have to give this information to the IIT-PAVE.
Please join later.
So how many layers is this one? You have to tell me. I'm not going to tell you.
It is 2 layers.
No, 3 layers, isn't it? Layer 1 and layer 2. We have to give the subgrade as well.
Okay. Then it is.
Okay, 3 layers. Okay. So first layer elastic modulus is 3000 megapascals. Second layer Poisson ratio is 0.35. Thickness 190.
It is 3000, I think.
Oh, sorry. Yeah. 3000. And elastic modulus for second layer is 200 megapascal. And Poisson ratio of 0.35 and thickness of 480. Okay. And elastic modulus of layer 3 is, which is subgrade 62 and Poisson ratio of 0.35. And wheel load remains the same, which is we said here 20,000 kilonewton, and tire pressure 0.56. And how many analysis points we need? 4 analysis points. Here you can see 4 points we have written. So 4 analysis points. What are those depths? Z is 190 and radial distance of 0. 190 and 155. 670 and 0. 670 and 155. And obviously we want to select wheel set, dual wheel set. So I click on submit and they run, and these are the values. Now, so which values we are interested in? Can you tell me? So you can see here, as I said, from here I said like first one is, let's say, let us look into subgrade. We are interested in finding out these coordinate 3 and 4, 670 0 and 670 155. Okay, which is 3 and 4, 670 0 and 670 155. But which one we should look? We should look ones with lower, isn't it? Because we get the, we want at the top of the subgrade, isn't it? Which is the lower layer. We are giving the points on the interface. If it is on the interface, what it will give is the values at the top of the subgrade we are interested in, which is like it will give 2 analysis points. So now from this we are interested in compressive strain or vertical strain at the top of the subgrade. So either this value 0.231 or 0.244. Okay. Now which one should I select?
It's maximum 2443.
Okay, 2443. So which is 244 micron.
Yes.
Yeah.
Sir, can you please again repeat the analysis, sir?
No, from where you want to?
From input value, sir. Layer 1.
So let me go back. Just to give me 1 minute, okay? So say for example, I'm going to edit. So what is your question? You can ask me what you didn't understand.
So layer 1 input, sir.
So layer 1 input is 3000 megapascal, which we have calculated here, which we have written here. From the IRC 37. So I'm just opening IRC 37 for you. Okay. So IRC 37, here it is given 3000 megapascal or tested value, which is less. That is what we have taken, 3000. And Poisson ratio 0.35, 190 thickness, whatever we calculated. And what is your other question?
That's it, sir. I was confused about the thickness, sir. The layer 1 thickness is 190 and layer 2 is 480. Am I correct, sir?
Yes, 480. That's why your depth is 670.
Yes.
Okay.
So layer 2 thickness will be 480, sir. We have to write there 480.
480.
Okay, sir.
Okay, which is I have written here 480. Okay. Now you can take what is the strain value that we have to take for the retting analysis. 244 micron. So maximum of we are looking at this value and this value. So let me write this one here. So for this pavement section, whatever the pavement section we have analyzed, the strain value, vertical strain value at the top of the subgrade, the maximum one, obviously we choose a maximum one, is 244 micron, micro strain. Okay, now can you tell me?
Maximum vertical strain is come below bituminous layer. That means before failure in rutting in subgrade, it will fail in below bituminous layer. Then how should we take maximum value in subgrade? Why not
No.
take
Say that again. Say that again.
Sir, it's a maximum vertical strain is coming below bituminous layer. That is 3257 into 10 to the power minus 3. But why we taking at subgrade layer? Because vertical you see coming below bituminous layer. That means the flexible pavement will fail in rutting at bituminous layer.
No, where is 3257?
That is bituminous layer, sir.
Bituminous layer, you are getting 325 micron. Yes, but that is not our model is in the according to IRC 30, the pavement design. What we are interested in is to protect the retting, isn't it?
Sir.
We want to look at the strain values only at the top of the subgrade. Okay, not at other locations. We have analyzed these two values to identify the tensile strain, only epsilon T value for these two, and these two value for epsilon V. Okay, so rutting in the granular layer we will not consider in the structural design. Okay, we assume that is taken care in terms of material mix design. Same, say for example, you might get more compressive. Definitely, you will get more compressive strain at the top of the bituminous layer as well. But still, we do not consider that because that we are not designing again. It's the resting in the.
So coming maximum at bituminous layers, below bituminous layer, not below granular layers.
No, because why it is coming is your vertical stresses are more, isn't it? If you look into vertical stresses, so this is sigma z. Your vertical stresses, compressive stresses are more in these, which is up to, you can see 0.07 megapascal, 0.07 megapascals. So you can see it is decreasing. Sigma z, if you look into vertical stresses, you have got around here the vertical stress is 0.09, whereas here it is 0.014, almost 5 times more than here. If your vertical stresses are more, obviously your vertical strains will be more. So if you remember in my very first or like first 2-3 slides, I talked about load distribution within the pavement. So it will distribute like this. So if you have a vehicular load, it will distribute like this. So if it is distributing like this, the amount of stress that is here is more than amount of the stress that is coming up to here, isn't it? So if your vertical stress is less here and it is more here, you sometimes get the more strain here, although your modulus is more. Okay, is that answered your question?
Yes, thank you.
Okay, no problem. So that is vertical compressive strain, vertical strain. Now we have to look for the tensile strain at the bottom of the subgrade. Sorry, at the bottom of the bituminous layer. Now, which values we should be looking for? We should be looking for both tensile and radial. Okay, so you should be looking for again, it is in the top layer. We should be looking for 1 and 3, not lower layer. So maximum of these 4 values. Maximum of these 2 and these 2, which is 4 values. So which is 145 micron. Okay. So maximum of these four values, 140 micron here, it is 92 micron here, 58 micron for this one, 145 micron here. So out of all these, I am selecting the maximum value which is 145 micron. So for this pavement, the maximum tensile strain I am getting is 145 microstrain. Now I input these two values into my fatigue equations, respective performance equations. So where are my performance equations? This is for fatigue and this is for rating. Can you tell me? You input your epsilon v value. Epsilon v value, how much did we get?
244.
You input 244 and tell me whether the section we have selected is satisfying our requirement or not. You input 245 and see if the NR is less than 131 or more than 131. So our value is 131. Our target value we have to design is 131 MSA. So you input this epsilon v here and calculate. I think, let me calculate here. Epsilon v is 0. So you have to input 0.000244. Okay. Hmm? So if you input, actually you should be getting 337.
Yes,
Has
sir.
anyone got 337
Yes,
MSA?
330.06.
337 MSA you get. Similarly,
Yes.
what is the tensile strain you have got? Epsilon T for the pavement. What is the tensile strain we have got from our analysis?
145.
So maximum tensile strain is 145. So basically micro strain. So if you input 0.000145, okay, into this equation, which is instead of epsilon t, you input this one. Obviously, just if you calculate m, I think your m will be, I think I should have those values. Your m will be
3:30 से 4 बजे के बीच आ जाना.
0.5 and C is 3.16. Okay, so your C is 3.16. So if you input your C value into here and epsilon T as 0.000145 and MR value 3000 megapascals, how much you are getting? NF? So let me input from my side as well. 0. I think you should get 145. Did you get 145? MSc. Has anyone got 145? Okay. Okay, so what does this mean? If we get 145 for the fatigue criteria and 316 or 337 for fatigue criteria, that means whatever thickness you are providing is satisfactory. So whatever design you have selected, so your NF number of cycles to failure for fatigue you found to be 145 million standard axis, and in terms of rating it is 337 MSA. Okay, the design is satisfactory. But what if it hasn't found? Like, you have to increase the thickness. Obviously, there are few rules which you have to consider increase or decrease the thickness. One is you have to always look for the constructability. Say for example, you just cannot select. Say for a good example is say this one 190. I have put here 190 bituminous course. Can I select 70 mm of SMA? Is that okay? 70 SMA and 120 dBm. So out of 190 my bituminous layer, can I select 70 mm SMA and 120 mm dBm? Is that okay as a design? What is the problem? You can tell me it is okay or not.
In design, we have to consider only 120 mm dBm only.
Why?
Because 70 mm MSA for the strength criteria, it is not. It should not be considered.
No, say that again.
For 70 mm, strength should not be considered. Only we have to take 120
No,
mm.
of course we can. No. We can consider both. Even SMA, both entire layer for analysis we have. But the problem is you cannot construct a 70 mm SMA. Okay, SMA. If you, what is the IRC? I think IRC. I don't remember the code. SMA you can go to. Let me check. I think somewhere you can go to up to 50 mm. So you can have a 40 to 50 mm SMA, not more than that. Your minimum thickness is 40, maximum is 50. So you cannot construct 70. So you always have to look for the constructability aspects as well. Okay. Those aspects you have to keep when you are selecting the thicknesses. While you are designing, always look, you will have a minimum lift thickness. Okay. Say you have 250 mm of granular granular base, for example, maybe you might not be able to compact entire 250. Say for example, maybe 250 is okay. Say you're having 350 mm of granular base. You should not be compacting all these 350 at a time. Maybe you can construct 175 and 175 as two lifts. But whether but say for example, you cannot have lift of 60 mm and 150 mm, something like that. So because 60 mm is too thin as a lift. Okay, those aspects you have to consider when you are selecting these thicknesses as well. Okay, other than what is said in IRC, you just randomly cannot choose the thicknesses. Always look for what is the minimum thickness, what is the maximum lift thickness and minimum lift thickness. Usually the rule of thumb is you want your lift thickness to be between 2.5 to 4 times the nominal maximum aggregate size. Okay, so you keep that mind. You can construct in two lifts or a single lift, but at least in the combination it should get the whatever the thickness that you are providing. Okay, that you have to consider. So hopefully for everyone it is clear how we design conventional bituminous pavement. Now let me go and discuss how we design if you have a cement treated base. Okay. So maybe before I go, I'll discuss one or two things treated base before I go to the examples, which I missed earlier. So minimum thickness of CTSB. So if you are providing CTSB, the minimum thickness is 200 mm. The grading 4 from the Moth table you have to adopt. So elastic modulus has to be 600 megapascal. Okay, you have to choose a 600 megapascal C as an elastic modulus. Okay, CTSB with grading 4 in IRCSB. This is the guideline for construction design and construction of CTSB layer. Having strength in the range of 0.75 is not recommended for the major highways, but it can be used for road with design traffic of less than 10 MSA. Okay. So Poisson ratio. So in IRC-SP 89, it has given two different these things. So you have to select according to that one. So the geosynthetics case, I'll come a bit later. So another point you can see is granular base. If there is a granular base on the top of, for example, if you have a pavement with say for example, you have a bituminous layer here, and on the top of that you have a granular base, and below that a CTSB, cement treated subbase, and you have a subgrade. Then in this case you have to choose resilient modulus of 350 megapascal. Okay, otherwise we use that equation 7.1 in which we use 0.2 multiplied by the H power 0.45, that equation. Because here we have a CTSB, we have to model these two as a separate layers in IIT-PAVE. That's why in such cases you can choose granular base as a 350 megapascal. Okay, these 2 points are for geotextile case, which I'll discuss a bit later. Okay, after next example I'll discuss that. This is a granular base and granular. So now what we'll do is we will discuss an example with cement treated base as a pavement. So let me again, this example is in IRC 37, but it is applicable for any. Okay. So this we discussed so far. Okay.
Sir, I have a question.
Yes.
Sir, this is the same procedure we adopt for the designing the soil treated with reinforced soil. Is the design criteria be same for the reinforced earth soil?
No. Are you talking about reinforced soil?
Reinforced
Or
soil, yeah.
reinforced granular base and granular subbase, geotextiles, geogrids.
No, reinforced for the sub base. For the sub base.
Sub criteria. Very small difference how we consider the modulus values, that I will discuss. Next problem is after this one is that one. Okay. Let me discuss first this one.
Is it same for the? Okay. Okay.
No. It is not same. The procedure and models and everything is same, but only there is small difference in selecting the modulus value for that reinforced layers. If you are reinforcing granular subbase, you have to choose modulus value slightly differently. What is that difference? I will discuss after this problem. Okay. So what we'll do now is, say for example, you have a pavement with so bituminous layers. You have a cement treated base. Okay. Obviously, if you remember, if you are having a cement treat bituminous layer, CTB, and CTSB, and subgrade. Okay, so this is bituminous layer. This one is what we say, crack relief layer. Okay, crack relief layer, which is always 100 mm. And we have a cement treated. I'm taking trial. I'm designing a pavement with cement treated base, cement treated sub base. Okay, this is subgrade. Obviously, as per IRC 37, we discussed whenever you have a cement treated base, we put either crack relief layer or SAMI layer. So the design is same whether it is a crack layer, relief layer, or SAMI layer. In the SAMI layer, you will not have this layer, only thing. So CTB thickness is 120 mm, and this is a trial thicknesses. Okay, and CTSB thicknesses of 250 mm and bituminous layer of 100 mm and flexural strength of 1.4 megapascal. So now maybe I will draw this in a fresh one. Let me open this one. So we have multiple layers. So bituminous layer. What is the thickness? H1 say 100 mm bituminous. And what is the modulus value? Should I maybe let me write H2 120. Sorry, we have a crack relief layer of H2 is
100 mm.
Yeah, so H2 is 100 mm. And this is CTB, cement treated base, which is H3 120 cement treated subbase. How much is this one?
250.
How much should we say? 250. H4 is 250 So let us write what information we need for all this one. Okay. What is elastic modulus for this one?
3000.
I'll write E1 here. E1 3000 megapascals and Poisson ratio 0.35. Okay, and for layer 2, okay. So it is let me show you where if you are struck. So I'll show you. So go to this table. You can see in this table for crack relief layer is it given granular interlayer. So which is 450 megapascal you can take. So 450 megapascal. Okay, and Poisson ratio is 0.35 and H3. What is cement treated base modulus value? You can see here the same table. Okay, cement treated base. What is how much? What is the one? 5000 megapascal, and similarly cement treated subbase 600 megapascal. Both Poisson ratios are 0.25. So E2, E3 how much? 5000 megapascal. And Poisson ratio, as I said, 0.25. And E4, 600 megapascal. And Poisson ratio of 0.25. Okay. What other information is required? Oh, sorry, I need to have E5 as well, isn't it? For the subgrade. Subgrade, what is the elastic modulus value I should use? What is the CBR of subgrade we assume?
7%.
Okay, for 7%, what is the elastic modulus value?
So
70.
Is it 70?
No, wait.
62, sir.
62. I think 62 is right because the previous example as well we use it the same, isn't it?
62.
It is not 10 CBR. So it is 62 megapascal. Okay. What other information is required for us now? So can you tell me at what locations we are interested in the mechanistic parameters? You have a wheel which is 20,000 20 kilonewton load and 0.56 20 kilonewton load and 0.56 megapascal stress. Now at what locations we need stress and strain values? Can you tell? So we need, this is at one immediately below this one, at the center these two, we need tensile strain at these two locations below the bituminous layer, and below the CTB we need at this location and at this location we need both tensile strain and tensile stress as well. Is it not? Why we need both of them? If you remember from yesterday's discussion, for CTB we have two performance models. Which is that one? So this is one performance model, which the input for this performance model is, the mechanistic input is tensile strain. Okay, the fatigue performance model for cement treated base. Similarly, for this one, the input parameter is tensile stress. Okay, at the bottom of the cement, at the bottom of this. So we need both stress and strain at the bottom of the cement treated base. Okay, so at these two locations, and also at the top of the subgrade, we need at these two locations vertical strain. Okay, here the horizontal strain and horizontal strain, horizontal stress. Now, can you tell me what coordinates we are interested in? 1, 2, 3, 4, 5, 6. What coordinates we are interested in? Let me write Z and the radial distance. So you can tell me what are those coordinates?
Sir, no stress parameter for CTSB. There? No
CTSB performance model is not there. Only for CTB we have performance model. Okay.
Coordinate
So
one is coordinate one is 100.
Okay. Let me. I didn't put what are ones and twos, isn't it? This is 1.
Yeah.
Use a different color. So this is 1. This
One is 100,
2,
0.
3, 4, 5, 6. Okay, 1 is Z of 100 and R of 0. Okay, and 2?
100, 155.
100 and 155. And 3? So 100, 100, 200,
200, 0.
320, 320, 0.
320, 0 and 320, 155.
55.
And this one, total pavement thickness. So 324.
570 0. 570.
Is it 670 or 570?
200, 320, 425,
570.
570 0.
Yeah, okay, sorry. 570 and 0 and 570 and 155. Okay, so we have entire information for pavement design for analysis. So we have all the information. We have elastic modulus values, Poisson ratio values, H's, and now you are familiar with them. So I'm not. So there are 2 times you have to do the analysis for CTB. Obviously, you have to check for allowable tensile strain for these two, which we discussed the same way how we did for the conventional. The same we discussed. So these 2 points, we need tensile strain. Okay, at these 2 locations, we look for horizontal strain and check for the whether the this pavement is satisfying the allowable strain requirement for your design or not. That we will check. Okay, I'm not going to discuss everything, show again, because we already did multiple times for other things. Particularly, we did it earlier as well. And here we need tensile strain criteria. Okay, which what you do is you input into this equation. Okay, you input the tensile strain. Reliability factor you use 1 because if it is an expressway, 2 if it is other roads, expressways, national highway, important roads, you use 2, and you use the elastic modulus value, and you use the tensile strain and check whether this satisfying your criteria or not. Okay, so this is also straightforward, so I'm not going to discuss that as well, because you just have to input that those values. Okay, and So we are interested in at these 2 points, horizontal strain and horizontal stress. Okay, so subgrade as well we know how to do. We can determine the epsilon v at these vertical stress at these 2 locations, and we input into Retting model and determine the whether it is satisfying the allowable strain criteria for the pavement design. So there is one additional one which we said, if you remember from my discussion, that is tensile stress. We do cumulative fatigue damage approach. Okay. How we do this, I will discuss. So if you remember from my yesterday's discussion, so this is this expression, you got vertical stress, fatigue life of CTB material, which is the maximum repetition of axial loads class I. So what we do, sigma T by MRP is stress ratio, 0.8 stress. Okay, and we take one tandem axle taken as 2 single axes and 50% tandem axle, 1 tandem, and what we do is we do cumulative fatigue damage. What is cumulative fatigue damage? I'll just show you now. Okay, one important thing I want to highlight is, which I didn't do that. So you will not do all of these at the same time. So you run the analysis for this one as one analysis. This one you have to do multiple times. Okay, this one as one. Okay, because here for these two the stress is 0.56. Okay, but for these two, which is at the bottom of the CTB layer, you have to use 0.8 megapascal as a uniform contact stress. Okay, so this is 2, and then you check for you run the analysis using 0.56 megapascal and check for fatigue in the bituminous layer and retting in the subgrade. And second time you run using the analysis using 0.8 megapascal and input these two analysis point, and whatever tensile strain, maximum tensile strain you got, you input that into the fatigue model for the CTB, the model number 1, and check for the criteria. And the third step is to check the cumulative damage whether it is following. So what exactly that I will discuss in next 5-10 minutes. Okay. So what you do in that case is, I'm not running the software because we have seen 3 or 4 analysis. What you do is you input all these inputs. Okay, all these inputs into the software, except you will not do the input 0.8 megapascal. Okay, the stress what you will be inputting is actual load that is going on to the pavement. Okay, so what are those values? I will tell you. So for that, what you need is you need axial load spectrum. Okay, this is axial load spectrum. Okay, say we discussed how we get the axial load spectrum. So this is single axial loads. From the axial load survey, you obtain the single load spectrum. Say for example, from 185 to 195 category, we got 70,000 and so on. Okay, and the tandem axial, these are the repetitions you are expecting. And for tridem axial, these are the repetitions that are you are expecting. Okay, so then what you do is, so this is 185. So you take intermediate value. So what is intermediate value? It is 190 kilonewton. So you can see 190. 70,000, whatever we take, and what we do is we input the values. All the values are same. Okay, so if you for 190 kilonewton axle load, what you do is, so all these values will be the same. Whatever you are taking, all these values will remain same, except and also locations. So your locations will be these locations. Okay, 320 and 321 for 150. Except what you do is your stress will be, you will be taking, say for example, if it is a single axle, it will be 190 kilonewton axle. It is an axle load, isn't it? 190 is 190 axle load. So what you will be doing is, then what is the single wheel load? Can you tell me what is the single wheel load? (190 divided by 4), isn't it? How much is this one?
47.5.
7.5.
So that will be your wheel load. Okay, maybe I'll just show you an example. Let me open the, just opening. Okay, so so what you do is you input 47.5 megapascal, sorry, 47.5 kilonewton as wheel load. Okay, so your wheel load analysis is single wheel load is 47.5 kilonewton load, and your stress is 0.8 megapascal, and you run the analysis. So 40 on each load you get 47.5 kilonewton wheel load, and you run the analysis with 0.8 megapascal and identify the maximum tensile strength. Okay, so at these two locations, at what tensile stress, okay, you will have only two numbers, one number here, one number here. Say maybe I'll open a file, although this file is not for the problem we are discussing. What you will be looking is these two numbers. Okay, these two numbers for that particular coordinate. So sigma t and sigma r. So in general, at 2 we discussed about 2, so you will have 4 coordinates. Out of those 4 locations, rather 4 numbers, you choose the maximum value, and what you do is so that value is, for example, you got 0.7 megapascal. Just an example, I'm saying you got 0.7 megapascal. Then your modulus of rupture value, how much is given? From our example, modulus of rupture 1.4 kilonewton megapascal, 1.4 megapascal. So you divide that by, so this is sigma t divided by modulus of rupture, okay, which is 0.7 divided by 1.4, which is 0.5. Okay, so we input this 0.5 into our fatigue model. If you remember our fatigue model from the IRC 37, sorry, this one. So see, we already calculated 0.5 here. If you input 0.5 here and calculate the number of cycles to failure, what we get is this value. Okay, I think it is 0.5 into 5.2 into 10 power 5 number of cycles. This is NF. Then because of this axle loads, what is the fatigue load that is consumed? That is basically you have 70,000 of these axle load group. Okay, and actually if what is this number 550 to what is this number actually 0.5 MSA. Okay, so these number of vehicles go on to the pavement. The pavement will be completely damaged. Okay, 100% damaged, but only 7,000 of such vehicles have gone on to the pavement. What does that mean? So 70,000 divided by this 0.526 power 10 power 6 will give 0.13. Okay, only 0.13% of damage has caused by this one. Similarly, if you run the analysis for other as well, say for example, if you take 90, run the analysis for 180 by 4, how much is that? 45. If you input wheel load of 45 kilonewton and 0.85 megapascal uniform stress and run the analysis, you will get 0.67 stress. And if you input that into fatigue model, you get I mean using MRP as well, I mean modulus of rupture as well, you will get this number. This is the if this load group of vehicle runs these many number of times, 100% of damage is caused to the pavement, but only 90,000 of such vehicles are going. So it is 90,000 divided by this number will give this one. This is the fatigue life consumed by this load group. Okay, so basically what you do is you run the analysis for each load group, all these load groups, and what we do is we sum up all these values. So 48% of payment life is consumed by, we have done only for the this one single axle loads. Okay, we have run this analysis for only single axle loads. So 48% of load is what we say life is consumed by single axle loads. Now we have to run the analysis for tandem axle loads. Okay, one important thing, if you see tandem axle with what is the intermediate value, 400 kilonewton axle load, so which is having, I think it is 200,000, 2 lakhs vehicles are going. But there is one small thing you have to remember. So that is 400, we have seen 400 kilonewton axle load group. So this is 400, but tandem axle means there are 2 axes. But so in each we have to assume, because our model is only for the single axle, so you have to divide that one. Okay, which is 200 kilonewton on each wheel. Now how much you put? 50 kilonewton wheel load. Okay, wheel load of 50 kilonewton and stress of 0.8 megapascal, and you run the analysis and determine the stress at the bottom of the CTB layer, which is 0.73. And if you calculate the stress ratio, which is 0.73, our modulus of rupture 1.4, you get 0.53. But one thing you have to remember is, because it is a tandem axle, we have divided the tandem axle into 2. That's why your reputations have been doubled. If you see the actual reputations of this tandem axle is 200,000, but because reputations has doubled, it is 200,000 has become 400,000. You have to double it. Okay, and run the analysis, and you can see the fatigue life consumed is 1.76, which is 176 already failed, just because the 400,000 of tandem axles of 400 kilonewton load group runs on this one. Payment has already failed. Okay, so from this number itself we can say the thickness we are providing is not sufficient. Basically what you have to do is you have to run for all these groups. Okay, Similarly, for the tridem axle, what we do is we divide this 600 into 3. Okay, so your axle will be carrying only 200, and your load reparations will be multiplied by 3, and you run the analysis. You can see 46 is consumed by this load group. So you have to run the analysis for all these load groups. Basically, you have to run the IIT-PAVE for all these. Maybe if there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, all these, and all these load groups 12, all these load groups 12. So 36 times you have to run, and the find out the what is the fatigue life consumed by each of these load group. You have to find out and sum up all of them, and if that sum has to be less than 1. If it is greater than 1, the payment is not going to be safe. Okay. So this is about if you are having a cement treated base as a payment layer. This is what we run the analysis. Hope it is very clear. But if you have any questions on CTB analysis, I can take questions for 1 minute. Maybe I'll take because today I'll be finishing, so this is my last lecture. If it is okay, I can take another 10-15 minutes to conclude I want to touch on some important points, which is one related with use of geotextile. Okay.
So 190 kilonewton single axle load is the maximum limit.
No, so if you are having say axle loads more than that as well, you have to include this. This is a example data. For this data, you have more single axle with 190 kilonewton. It is not a limit. If you are having axle loads having more than 190 single axles as well, you have to include into your axle load spectrum.
Okay, sir. And the second question is, when we are going for the analysis of that BT less layer with that tire pressure of 0.8 megapixel and load. So in coordinate place, when we are going to run the software, so only 3-4 coordinate data will be input, or other data
no,
also.
for the CTB cumulative damage consumed data, only 3-4 whatever examples I have shown, only 3 at that location only is required. For the if you are running for other layers, for bituminous layers and subgrade bituminous layer fatigue and subgrade, you need other points. But for the fatigue consumer, we are interested only at the bottom of the CTB layer. So only 2 coordinates is required.
Only 2 coordinates and 2 layers, including subgrade.
No. You have to include all the layers.
All the layers. Okay.
You have to, in the analysis, you have to include all the layers. Okay, all the layers you have to include. Okay. Any other questions on CTB? Because it is the most complex design method in IRC37. Rest of them are straightforward because this involves all the types of payment designs. Okay, if you understand this one, it is okay. But if you have any questions, you can ask. Okay, now I'm going to the last one I wanted to discuss is what if you are having a geotextile membrane. Yeah, I mean if you are having geotextile or geograde for reinforcing the payment. So this is my last topic I'll be discussing. So let me check if I have missed any. So I discuss this. Okay, these charts anyway, you know. Okay, there are 2 topics actually, but I won't take more than 10 minutes. Okay, I hope it is okay. But these 2 are like not regular payment design methods or anything. But what if you having a geogrid in a payment? How you address that one? And there is one concept called long life payment, which is straightforward. Okay. Okay, so I'll explain the concept first, and then I read out this one. Then you will understand better. So, for example, I'll open a fresh. Say now you decided to use so you have a bituminous layer, and this is granular layer, and subgrade. Okay, so you decided to use a geogrid or say geocell. You want to reinforce this layer with a geocell for whatever reason it is, maybe because of you want to reduce the thickness or whatever reason. So how we deal in terms of pavement design as per IRC 37. So if there is no geocell, what we do, it is a normal procedure, isn't it? The only thing is you choose elastic modulus MR equal to 0.2 multiplied by H power 0.45 into MR of support. Okay, so if you are but you are having a geo cell, so what we do is we separate this one as a one layer and this as a separate layer, and only difference will be what is the modulus values we choose for this layer and this layer. So I think it is IRC SP59 if I'm not wrong. Let me check the number. IRC 59. So IRC 59 is about the geogrids and geotextiles in general. So when they are used, the guidelines is that one. So what it suggests is to use a modulus improvement factors. Okay. So what those are is, say if you are having a geocell here, the modulus values we choose is, what we do is granular layer. Before coming to the granular layer, first we have to decide what is the modulus layer for geocell. Geocell reinforced GSB. Okay, so you have a GSB here, granular base. So for GSB modulus, what we do is, how we are converting the granular layer, we use the same formula, this formula, but H, in earlier discussions we said H is sum of these two. Okay, but here what we use is H is only the thickness of granular subbase. Okay, and MR is the same as this one, and you determine MR value. Okay, MR support, and say for example you got 140 megapascal. Then what we do is we multiply this one with 140 with the IRC SP59 gives the modulus improvement factors which range between 1 to 1.3 depending on the CBR of the subgrade. They suggest 1 to 1.3 modulus. I mean, I think more than 1.1 to 1.3 or some values. So you can go to IRC SP59 and choose the modulus improvement factors. If it is 1.2, you multiply this one with 1.2 and you get certain value. Say if it is 140 multiplied by 1.2, how much is this one? 20 plus 10. Is it 170? Is that right? How much is 140 multiplied by
168.
168. Okay. So you choose 168 as granular subbase, although you get 140 because you are reinforcing with the geocell. Okay. This is, and the next step that is also how we choose the granular base modulus. So how we choose the granular base modulus is, now you have got a layer of 168 modulus of geocell, and what we do is we assume from here how we have done the effective modulus of subgrade similarly, but we consider this as one layer. You have one layer of 168 megapascal layer, which is reinforced geocell reinforced GSB, and you have a subgrade with certain CBR value. Say if it is 62 megapascal. Okay, and how we know how we can determine the effective CBR of two layers. Say we put a 40 kilonewton load and 0.5 analysis, and we find out the deflection, and we input into the formula we discussed and find out the effective modulus of this one. So that modulus we will use for assign for the granular base, and then design it as a conventional pavement. This is how we handle if you are having geo section, I mean geocell or geogrid reinforced granular layers. Okay. So if you have any questions, I can take a couple of questions on this one. Before, there is one final thing I want to discuss, which is a straightforward thing, which I already discussed how we handle the wrap material when we are discussing. It is a straightforward. But one is the long life pavement. So what is long life pavement is? So have you heard about term endurance limit? So for example, I'm applying some stress. Say this is a stress ratio or strain. Some strain or stress ratio on my y-axis and number of cycles to failure on x-axis. So if you draw for a material, okay, a line, fatigue line. So with the decrease in the stress ratio, with decrease in the stress or the applied strain, your number of cycles to failure increases. But there is a point above which it will be infinite. Okay, it will be almost infinite. If the strain is sufficiently low or stress ratio is sufficiently low, the number of cycles to failure is infinite. Okay, the fatigue line will be something like this. This limit we call it as an endurance limit, either stress ratio or tensile strain, depending on what type of material we are considering. Okay, say for example, if it is a bituminous layer, our analysis is about tensile strain. So for bituminous layer, what people have found out is this is approximately 80 microstrain. Okay, 80 micron. So what it means is, if you are designing a pavement such that, so this is a bituminous layer, this is a granular layer, and this is a subgrade. So if you are designing a pavement, okay, sufficiently thick, very sufficiently thick, such that your tensile strain at the bottom of the bituminous layer is less than 80 microstrain, then your pavement is never going to fail. That is what the long life pavement is. So the design will be, how you design is, you make the bituminous thickness sufficiently such that your tensile strain is less than 80 microstrain, then that we call it as a long life pavement, which is given in the IRC 37. So with that one, I conclude. But if you have any questions, I can take some questions from you.
I'm having a question. When
Yes,
to
please.
choose our regular pavement or the CT SB or CTB pavement?
So it is see, there is no such thing. It is only coming to your economics. Okay, which one is less expensive? That is what you choose, isn't it? Usually these days people are using the cement treated base, because if you are using cement treated base, strong bases, your overall payment thickness will come down. That will save some money to the contractor.
Okay. And one more question for now, giving input in the IIT-PAVE software for CTSB.
Can you give me just 1 minute? Okay, just 1 minute. Sorry about that. I had to take that call. Okay. Can you tell me what was your question?
Suppose how to provide the input for the. I'm asking completely. Can you give me one more time? Explain. Means first, my tire pressure will be different, right?
Your tire pressure will be 0.8 megapascal, and wheel load is different, tire pressure is different. So wheel load will be I'm just giving you that, opening that example for you. So for example, you are running the analysis for single axle loads. Okay, from your axle load spectrum, this is a single axle load. So your axle load is 190 kilonewton. So 190 kilonewton is, what is the wheel load? Axle, what is our standard axle? Our standard axle is dual wheel
45
axle. So it is carrying 190 kilonewton. Okay, so each wheel load, how much it carries? 47.5, isn't it? So my wheel load will be 47.5 kilonewton, and contact stress will be standard 0.8 megapascal. And you run the analysis, and your analysis locations will be at the bottom of the cement treated base. You can ask me what is your exact question. I can repeat that. Is that
what means how to combine it? How to combine it? Means combining the bituminous also and this one also.
In your analysis, as I was saying, in your analysis, you will input all these layers. So this is the example I was discussing. In the analysis, you will input all these layers. It is not that you are inputting only CTB layer. You have to input bituminous layer. You have to model the crack relief layer. You have to model CTB. You have to model CTSP. But the analysis point will be only these 2 points, 0.4 and 0.3, and determine the tensile stress at the bottom of this one. And we input these tensile stress into the fatigue model I have shown to you earlier.
If you have like 5-10 minutes, you can just show it on the IIT-PAVE software. Just input it.
I can do that for you, but let me take questions for others, and I'll definitely discuss that with you. Let me take other questions, okay, and I'll come to you.
Okay.
And whoever has the same question, I'll be running this in the IIT-PAVE software after this one. If you still wants to be there, you can be there, others. But others, if you have any other questions, if you have to leave for them, let me take their questions and then I run this for you. Okay.
So what are the geocell material we will use for which our GSP modulus factor will be improved?
No, there are many permissible ones. You have a geograde, geocell, okay, geotextile. So if you go to IRC SP59, it has given all the what are the permissible materials that you can use for reinforcement of the individual layers. Okay, so for each of them, they have also they have given the modulus improvement factors as well. So if you are using, depending on the CBR, modulus improvement factor depends on the CBR. If CBR is more, the modulus improvement factor is less. If CBR is less, CBR of that respective material. Okay, if CBR is less, the modulus improvement factor will be more.
Sir, is it required for run all the analysis for all kind of single axis load for CTB?
Yes, you have to run for every axle load group. Okay, so these are the axle load groups for the single axle. we have to run for 190 separately, 180 separately, 170 separately, 160 separately, 150 separately, 140 separately, everything separately. This is only for the single axle. And similarly, you have to run the analysis for the tandem axle as well. So you have here tandem axle group. For each load group, every load group, we have to separately analyze. Similarly, tridem axle load group as well, we have to run separately. Okay.
Yes, sir.
Any other questions? Before I explain once again running this in the IIT-PAVE software. Okay, so I'll maybe quickly explain this in IIT-PAVE software. So let me open this one so that it will help me. So we have these inputs. Okay. Back to it. Now you can help me inputting this one. So how many layers I have?
Five layers.
You can tell me how many layers.
Five layers.
Okay, 5. Yes, 5 layers. So I select 5 layers. Then what is the elastic modulus of first layer? Let me drag this one.
3000.
So yes, 3000. See, remember, I'm not showing you how to do the analysis for bituminous base because that we already covered in this one. I'm just showing only the fatigue analysis, the stress and the cumulative damage analysis for the CTB layer. Other analysis also you have to do. As I said, you have to do 3 different sets. I have drawn here. So this is first set for the at the top of the subgrade and the bottom of the bituminous layer at these 2 locations, and these 2 locations we have to find out and put in the respective models. And we have to do for the one for the tensile strain, we run the analysis and see whether it is okay. And the last one is cumulative damage, we have to do repeatedly. Okay, what is that? I'm showing only the third step of CTB design. Okay, so 3000 and Poisson ratio 0.35 and thickness
100 mm.
100 mm, yes. And elastic modulus layer for 2
50.
So which is 450. 450, Poisson ratio 0.35 and 100 mm. Okay, and H3 which is CTB layer or CTB layer 120. Okay, Poisson ratio of 0.35.
It's one.
Okay.
5,000.
Sorry, 0.25. CTB is 0.25. Okay, and
Elastic
thickness.
modulus.
Oh, sorry, I input it. Okay, elastic modulus how much? It is 5,000.
5,000, sir.
0.25 and thickness of 120. Similarly, this elastic modulus of fourth layer is 600 megapascal. Poisson ratio of this is CTSB 0.25. 0.25 and thickness of 250. Okay, and subgrade modulus how much we got?
62.
We haven't got 62 megapascal. Yes, we did calculate 62 and Poisson ratio 0.35. Okay, now tell me, say now we have input everything. Let me go to the first, I'm analyzing the first axle load, which is 190 kilonewton single wheel load, 190 kilonewton single axle. For each wheel, it is 47.5 kilonewton, isn't it? So 190 is carried by 4 wheel loads, but for each wheel load, it is 47.5. So I have to input 47,500 megapascal here. Okay, and a tire pressure, how much I have to give?
It depends on coordinates.
Sorry, tire pressure is not depend on the
0.8.
coordinates, isn't it? Okay, 0.8.
0.8.
0.8. Okay. And how many coordinates we need? You can see from the figure, we need 2 coordinates, isn't it? 3 and 4.
Yeah.
Okay, so I am selecting only 2. So what are those coordinate numbers we have
320
here?
0. 320 0.
Okay, 320 and 0 here.
And 320 155.
320, 0 and 320 and 155. Okay, so we have input everything. Okay, now let me 2 wheel set, dual wheel set, submit, and we run the analysis. So we are okay. So now tell me which values I have to look. We need stress value. Okay.
Sigma T and sigma R.
Sigma T and sigma R, but which lines? First and third, or third or fourth, second and fourth? Because L is lower layer, isn't it? We are interested in bottom of the top layer. So we have to look into the first and third line. Yes or no?
Yes, sir. No.
So we are interested in maximum of these 2 and these 2. What is the maximum value of all these 4 points? By looking at it, so these 2 points and these 2 values. What is the maximum value of all these? Which is 0.699.
995.
Okay, which is 0.7. Okay. So my sigma T will be 0.7 megapascal. Okay, but what I need is sigma T by modulus of rupture. Okay, so if we see our fatigue model, okay, our input will be sigma T by modulus of rupture. What is sigma T by modulus of rupture? See, our sigma T, we got 0.7 megapascal. Modulus of rupture, according to our example, it is 1.4 megapascal. So it will be approximately 0.5. If you input 0.5 into this one, the NF you get will be, you can calculate if you have time, but I have that number here. Okay, if you input that 0.5 into that equation, this is the NF you get. Okay, this is the NF you get. Okay, that is NF. So what this NF is saying us is, if 190 kilonewton axial load run on a pavement that I have shown, okay, whatever we have analyzed, run this, what is this number? Is it 5,26,000? Yes, 5,26,000 times. If 190 kilonewton standard, 190 kilonewton axle, dual wheel axle runs on a pavement that I have designed, the CTB layer will fail. But it is running only 70,000 times in my design life. Entire design life, it is only running only 70,000 times. What does that mean? 70,000 divided by this 5.26 10 to the power of 5 is 1.3. Only 13% of life is consumed because of this one. But we have others as well. We have to see what are other axial load groups also consuming the life and assess whether entire. So all these values together, sum of all these values, plus you have to run the analysis for all these load groups as well and these groups as well. all together. So in total, we have 36 different load groups. So fatigue life consumed by all these 36 different load groups has to come less than 100, less than 100%. This is 13%. It should be less than 1 or 100%, whatever it is, how you do. Okay. So is that clear?
Yes.
Yes, sir.
Okay. So any other questions? No?
Sir,
Book also. It is saying that this is failed. The CTSB and CTB.
It is failed because it is failed because the single axle loads has consumed 48, but even if you see this one, 176 load has been consumed by this one. So only it can take only 2,28,000 of these tandem axle with 400 kilonewton rather 200 kilonewton. It is only it can take 228 times. So rather it is 200 kilonewton axles, because we are dividing it by 2. Only such for 400,000 it can it cannot take, but it can take only 228,000, which is 2,28,000 times only it can take, but it is flying almost 400,000 times. That's why because of this itself it has damaged. Okay, the sum of all these damage has to be less than 100%, but here itself, because of this load itself, it is 176%.
Sir, why a long complexity in process in
CTP design? Because that is how we have to design the cement treated materials. Okay, if you see the concrete pavement design as well, we run the similar analysis, because how the cement treated materials behave, and also models are not available because for the flexible pavement we have collected a lot of data and models were developed, but the concrete pavement, because we are borrowing from someone else, we had to adopt such approach.
So for technical, we are going to this kind of combination.
Because it will save money, because the payments are going to be thinner, because you are using strong base rather than granular base, which is having a modulus of around 300 or 400. CTB have very strong base, isn't it? So your thickness will come slightly down.
Okay.
Your entire thickness of the pavement. Same pavement, if you say for the same line, if you design conventional pavement, it will be very thick. But financial reasons, we are doing this one.
Sir, sometimes we provide selected sandwich layer beneath the subgrade. The analysis remains same as for
sandwich layer. Why we provide beneath the subgrade?
To improve the quality of bearing quality of the soil.
Below subgrade? No, I don't think so. Maybe on the granular subbase below, or you can provide, but not below the subgrade. Maybe sometimes you can design subbase with fly ash or something, or you can stabilize the subgrade.
Yeah, that is quality stabilization. Then the analysis will remain same. We consider the effective modulus of elasticity.
Yes,
for the
analysis will remain same. Instead of CBR, soil CBR, you take stabilized soil CBR.
Sir, one more question. Now, if you are using CTEB or CTSB, timing layer or the granular crack layer, right?
Yes.
How to choose between these both? Which one we should? In practical, which one
to
we should
choose? See,
choose?
many of these questions just is based on the cost, isn't it? It is not a there is no technical answer or a right answer for this one. It is just everything comes down to cost. What is the cost of the payment? Okay, if the SAMI people decided to use SAMI layer, and if they found because SAMI layer is a required bitumen and aggregate, maybe it might be slightly costly. Okay, but it everything comes down to the which one is cheaper. Because in IRC 37 assumes all payments perform similar, although because we are, although that is assumption, because we do not have sufficient, because semi-treated bases and cement-treated subbase and SAMI layers, all these payments are only recently constructed, isn't it? We do not have sufficient data to say which one performs better. Okay, but the design philosophy is to it performs similar. Okay, but mostly it will come down to which one is less expensive. So if you do not have any questions, I will take leave. Thank you for joining.
One question.
Thank
Yeah,
you, sir.
if
Thank you, sir.
problem, if it's okay if we contact you in practical, suppose.
It is okay, but if you can ask now as well if it is okay with others. Okay, because others might have same question, and okay then you can I will stop sharing my screen.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Okay, thank you.
Thank you so much, sir.
Thank you, sir. Thank you.
Thank you, sir. Thank you very much, sir.
No problem. No problem.
Discussion, Dr. Kuna.
Thank you, sir. Thank you. Thank you for giving opportunity.
Very good interaction, participants. So your presentation is over. You have not able to hear me.
Hello, sir. Now I can hear you, sir.
Am I audible? Okay. I said very good interaction, very good discussion by the participants.
Okay. Okay. Hopefully they understood something.
So
they
your
learned
discussion
something.
and the presentation is over?
Over, sir. Over.
Okay. Anything to be discussed more by the participants?
If they have any questions, I can answer.
Okay, I think enough discussion has taken place. Thank you very, very much. Since last 3 morning, every half day you are taking the lectures, and you have covered IRC 37 in detail, including the practices and case studies, design case studies. So I thank you very much, and thanks to the participants. We will meet tomorrow. We are closing the session over here. Thank you very much. Look forward to
I
have
will
you
share
again.
you the presentation slides as well, sir, today evening. Whatever I have discussed,
Material,
you can share with the students.
PPTs and anything, whatever you wish to share, please share.
I'll share all the material I can. Okay.
Thank you, sir.
Okay, sir. Thank you.
Thank you, sir. Thank you, sir.
Thank you.
Okay, sir. Thank you so much.
Thank you.